Hello and welcome to the following lesson on the ideal gas equation, which is part of the thermal physics topic in AQA A-Level Physics. So in today's lesson what we're going to do is try and understand and describe the ideal gas equation. So if we've been successful and learnt in this lesson, we should be able to define what an ideal gas is with its assumptions, discuss whether the experimental gas laws can be combined and if so how, distinguish between molar mass and molecular mass, and then finally use the ideal gas law to solve problems with gases. So we're going to be looking at the following part of the AQA A-Level Physics specification, 3.6.2.2 ideal gases. Now the three experimental gas laws are as follows. Boyle's law, which is where pressure times by volume is equal to a constant, i.e. pressure and volume for a gas are inversely proportional. The second law is Charles's law, which is volume over temperature is equal to a constant. In this case, volume and temperature are directly proportional. And finally you've got the pressure law, which is pressure over temperature is equal to a constant, i.e. that the pressure and temperature for a gas are directly proportional. Now we can take these three experimental gas laws and we can combine them into one equation, which is that P times by V over T for a gas is equal to a constant. Now this constant is just a value which links these three properties for any gas. Now we can then use this to then derive a very useful equation to compare the pressure, volume and temperature of a gas from when it's changed from one state into another. So it's an equivalent. So we can say P1V1 over T1 is equal to P2V2 over T2. Now please remember, in this equation and for every equation we look at in this lesson, the temperature in this equation must be given in kelvins. Now for this particular equation to be used, we've got to make an assumption, and we've got to say that the gas is acting as an ideal gas. Now this is one version of the ideal gas law. Now this version should be used if you're evaluating a change or a difference in a property of a gas. Now you might ask, what is an ideal gas? Now an ideal gas is a theoretical gas that obeys the experimental gas laws at all pressures and temperatures. Now in this case, the internal energy of an ideal gas is only dependent on the kinetic energy of its particles. The particles do not have any potential energy. So whilst we say an ideal gas is one that obeys Boyle's law and Charles's law and the pressure law under all conditions, in reality no real gas is an ideal gas under all conditions. Under the conditions of low pressure and high temperature, real gases will obey Boyle's law and behave in an ideal manner. But if you have a high pressure or low volume and temperatures near to a gas's boiling point, real gases stop behaving ideally and no longer follow Boyle's law. The reason why this is because in these conditions the gas's molecules or atoms occupy a significant proportion of the gas's overall volume, which means it can no longer be acting as an ideal gas. Now it's important to note that the particle model of matter always shows an ideal gas view of a gaseous state. But remember, this is an assumption and gases are not actually ideal. Now ideal gases have several key assumptions attached to them. Now here are the ideal gas assumptions. Number one, all gas particles are identical to each other. Number two, all particle motion in a gas is continual and random. Number three, all particle motion in a gas follows a straight line. Number four, all molecules in a gas have a negligible volume compared to the volume of the container, i.e. the container that the gas is in is much bigger than the particles of the gas themselves. Assumption number five is that the gravitational force and the electrostatic force between gas particles does not exist. Number six, the internal energy of a gas has no potential energy store, only a kinetic energy store. Number seven, the Newtonian laws of motion are obeyed by particles in their motion, and there's enough molecules in a gas to apply statistical laws. Number eight, all particle container collisions are elastic, so when particles collide with the container that they are in, the momentum and the kinetic energy of those particles is conserved. And finally, the time between each collision with the container surface is much longer than the duration of a collision for particles in a gas. So when describing an ideal gas, we assume the gas has the following properties, which is to ensure we can derive an equation to describe the property of a gas. The molecules of a particular particular gas are all identical, the internal energy of the gas is entirely kinetic, all collisions between molecules and the walls of the container of the gas are completely elastic, Newton's laws of motion apply, the molecules take up negligible volume of the gas, gravitation and electrostatic forces can be ignored, the motion of all molecules is random, and all the molecules travel in straight lines. Now, like mentioned before, in reality, no gas is ideal, so it's a mathematical assumption we use to make the formulas of ideal gases easier to handle. So like we mentioned before, we can combine the three experimental gas laws into one equation. PV over T equals a constant. Now, ideal gases all behave in the same way, so we can say that they'll all have the same constant, and we can assign a letter to this constant, which we give as R. Now, R is what we call the molar gas constant. Now, R has a value of 8.3 joules per Kelvin per mole for all ideal gases. So this tells us that if the volume and temperature of a gas are kept constant, then the pressure depends on R and the number of particles in the container. So we can then therefore say, we can write this in our equation by saying PV over T is equal to NR, where N is the number of moles in the gas. Now we can rearrange this to give the standard form of the ideal gas equation, which is PV is equal to nRT, where R is the molar gas constant and is 8.31 joules per Kelvin per mole for all ideal gases. T is the absolute temperature of the gas in kelvins, P is the pressure of the gas in pascals, V is the volume of the gas in meters cubed, and N is the number of moles in a gas. Now, what do we mean by the term mole? Now, a mole is the amount of a pure substance containing the same number of chemical units, either molecules or atoms, as there are atoms in exactly 12 grams of carbon-12, which is 6.023 times 10 to the 23. So basically, a mole is a measure of how many particles there are. So 1 mole is when there are 6.023 times 10 to the 23 atoms or molecules or particles of a substance. So a mole is just a term used in language to describe an amount, like the term single, double or triple would be. So there are many examples of getting 1 mole of a substance. So you can see on the following images 1 mole of that substance. Now, different atoms or molecules of different substances are different sizes and masses. This is why different molar amounts can be different sizes and masses, as shown in these particular images. These are all 1 mole of that particular substance. Now, in 1811, the Italian scientist Amedeo Avogadro developed a theory about the volume of gases. So Avogadro's law states that equal volumes of different gases at the same pressures and temperatures will contain equal numbers of particles, i.e. the same number of moles. So if you have the same volume of a gas, you'll have the same number of moles of a gas. So in mathematical terms, Avogadro's law is V1 over N1 is equal to V2 over N2. So we can express the number of moles in a substance mathematically. We can say that the number of moles in a substance is equal to the mass of the substance divided by its molar mass. Now, the molecular mass is the sum of the masses of all the atoms that make up a molecule of the gas. Now, this is given on the periodic table as the relative atomic mass, e.g. the molecular mass of carbon-12 is 12. Now, this can also be called the relative molecular mass when there are a number of atoms in the gas molecule. Now, this links to the molar mass because the molar mass is the mass that 1 mole of a substance would have. Now, when this is given in grams, the molar mass is the same as the relative molecular mass for a molecule. So, for example, the relative molecular mass of O2 is 32. So this means that the molar mass of O2 is 32 grams. But please be aware that the molar mass can sometimes be needed in a question in kilograms instead of grams. So just be mindful of this. Now, you can also write this equation in another form. We can say that the number of moles is equal to N over Na, where N is the number of particles or molecules in a substance and Na is Avogadro's constant, 6.023 times 10 to the 23. Now, you can use either of these two equations to work out the number of moles in a substance. It's dependent on the quantities you are given in a question. Now, the concept of ideal gases is then used to approximate the behaviour of real gases. Now, obviously, real gases can become liquids at low temperatures and high pressures. So we can use our Avogadro's equation to derive a new equation for an ideal gas. So like we said before, PV is equal to nRT, but we just looked in our previous examples of another equation for N. So we can then write that and substitute it in. So we can substitute in the value in our equation we use for moles and Avogadro's constant by now saying PV is equal to the number of molecules times by R times by T over Avogadro's constant. Now again, you can use either equation to work out a value of a gas. It's dependent on the quantities you're given in your puzzle. Now remember, if you are going to use either of these two equations, the temperature must be given in kelvins. So let's have a look at an example. A cylinder contains 400 moles of an ideal gas at a temperature of 290 Kelvin. If the volume of the container is 8 meters cubed, what is the pressure of the gas? So to answer this type of question, you would follow the following steps. So step 1, you would write out the ideal gas equation you would need to use with the values given in your equation. In this case, PV equals nRT. Step 2, rearrange the equation into the actual value you want to work out. In this case, pressure, P. So P is equal to nRT over V. Then step 3, ensure the temperature is given in Kelvin. Yes, it is, and sub in your values. So 400 times by 8.31 times by 290 over 8. You can then step 4, calculate your value to be 1.20 times 10 to the 5 pascals or 120 kilopascals. Now it's also important to notice that a scientist called Ludwig Boltzmann noticed that R and Na, which were given in our previous equation of PV is equal to nRT over Na, are both constants, so dividing one by the other will always give the same value, which he called the Boltzmann constant. Now the Boltzmann constant is the physical constant relating energy at the individual particle level with temperature, but it's important to note we can only ever work this out at a collective or bulk level because it's a statistical value, it's an average value. Now we represent the Boltzmann constant with the symbol K, and we can work it out by saying K, the Boltzmann constant, is equal to R, the molar gas constant, over Na, Avogadro's constant. Now all these constants, K, R and Na, are given to you in your examination formula booklet. Now K, the Boltzmann constant, is 1.38 times 10 to the minus 23 joules per Kelvin. So what that is telling you is that basically when you raise the temperature by 1 Kelvin, each individual particle will receive an extra 1.38 times 10 to the minus 23 joules worth of energy. Now remember, you can only use the Boltzmann constant when considering many particles. It's an example of statistical mechanics value. It's only true as an average of many particles. So we can then use this equation to then simplify our previous ideal gas equation. So when dealing with individual molecules of a gas, we can use a different constant because the molar gas constant is only applicable for n number of moles of a gas. So we can now say PV is equal to nKT, where n is the number of molecules of the gas and K is the Boltzmann constant, the gas constant for a single molecule. So our Boltzmann constant has now replaced the values of R and Na in the equation. So there are actually many forms of the ideal gas equation. Our most standard form, PV is equal to nRT. The form which has Avogadro's constant in, PV is equal to nRT over Na. The equivalence form, which is used when you've got a change in the value of a gas property, P1V1 over T1 is equal to P2V2 over T2. And finally, the Boltzmann form when you're considering the individual gas molecules themselves. PV is equal to nKT. Now please remember, these are all iterations of the same physics principle, the ideal gas equation. Now you can use any form of this equation in an ideal gas question. You've just got to look at the values given in your problem. So let's summarize what we've learned in today's lesson. The ideal gas equation is PV equals nRT for n moles and PV equals nKT for n molecules. You should should be aware of the Avogadro constant, Na, the molar gas constant, R, and Boltzmann constant, K. And also be aware of the terms molar mass and molecular mass. So if we've been successful and learnt in today's lesson, you should be able to define an ideal gas with all of its assumptions, discuss whether the experimental gas laws can be combined, and if so, how, distinguish between molar mass and molecular mass, and finally use the ideal gas law to solve problems with gases. So I hope you've enjoyed today's lesson on the ideal gas equation, which is part of the thermal physics topic in AQA A-Level Physics. Thank you very much for watching, and as always, have a lovely day.